All right. Welcome to this week's UTIG discussion hour. Today we're going to hear from our very own Brandon Shuck. Most of you know him really well. Brandon came here in 2016 and he works with Harm and Sean. And I think I'm just going to let him go ahead and get started with this talk. Dude, where's my ophiolite? Go for it, Brandon.
Awesome, cool. Yeah, so thanks everyone for tuning in. So yeah, a lot of the things that I'm going to be showing today were inspired by thinking about the results of a study that I've been working on, looking at subduction initiation along the South Island in New Zealand, and then thinking about the implications that those results have for metamorphic souls and ophiolites. So a lot of the things I'm going to be talking about today, I'm not necessarily like an expert on by any means. I'm going to be showing a lot of other people's work as well, and hoping that this can be more of an informal talk, and towards the end we can spark interesting discussion. So before I jump into anything, just want to acknowledge the fact that I'm showing a lot of things that other people have worked on. So I want to show my appreciation for my advisors, Harm and Sean, as well as collaborators in Caltech and in New Zealand. So in thinking about a talk about ophiolites, I was struggling a little bit thinking about where to start. And I know I've always been super fascinated by ophiolites, and it turns out that pretty much all geologists ever have been fascinated by ophiolites. And they have a really important fundamental role in our understanding of the Earth. So the concept of ophiolites goes way back into the early 19th century, long before plate tectonics, and was first pointed out by European geologists and the Alps, who noticed these green rocks and called them odd rocks. And later on in the early 1900s, there's a German geologist, Steinmann, who came up with this trinity that kind of defined the occurrence of ophiolites, and that there's a combination of peridotite, diabase, and radiolarian cherts. And in the early thoughts, these were thought to be magmatic products, and so they were suggested to form in these geosynclines, so these structural lows, and then later get incorporated into mountain belts and these geoanticlines. And so later there were a lot of observations that progressed our knowledge of ophiolites, and it wasn't until we started understanding things like sheeted dikes and mantle residues and fossil magma chambers that were occurring that led to this ophiolite model in the 1960s. And so that model was kind of officially inaugurated at a Penrose conference in 1972, where there was this layer cake stratigraphy for ocean crust that was agreed upon. And that's shown here, that we're all very familiar with, I'm sure. And the four things that were kind of agreed upon is that these sheeted dikes argue for an extensional seafloor spreading origin, that these are slices of fossil oceanic crust and mantle. So it was early on recognized that there's a mantle residue and melting products that form the crustal materials, and that there are fossil magma chambers, and that these materials must somehow be transferred over to the continents across plate boundaries. But there wasn't really any consensus about emplacement mechanisms or variations in the setting for its igneous origin. And actually a year later, there was a study that was on the Trudeos ophiolite, where this person proposed or did some analyses and showed that a lot of the rocks followed a calc-alkaline trend, and that it may have formed in an island arc tectonic setting instead of just a normal mid-ocean ridge. And of course, we've made light years leaps and bounds since then. So today we realize that there's a very diverse suite of ophiolites globally. And it doesn't just have this like classic layer cake stratigraphy that you saw before. Oftentimes there are some pieces that are missing. There are some pieces that are present. They're often heavily deformed and offset by faults and shear zones and other sort of metamorphic fabrics. And they're found kind of all over the place, although not in a large volume. And they've really been classified most recently into 5 distinct categories based off its igneous origin. And so those categories are continental margins, so like a continental rifting ophiolite, mid-ocean ridge type setting, plume, supra-subduction zone, and volcanic arc. So I'm gonna explain the supra-subduction zone here in a second, but just note that a large majority of these ophiolites under igneous origin have this subduction and volcanic arc signature, suggesting that there's a strong relationship between ophiolites and subduction zones. And this was first recognized that there might be a link between ophiolites and subduction back in the late 1970s, early 1980s from some studies, ocean expeditions that went to the Isubronan Mariana system. And they recovered some samples from the inner trench wall and forearc there. And what they found was a big surprise. They found ophiolitic material that was essentially Eocene in age sitting right next to the trench. And something that they found was a distinct rock type called bonanites. And these are essentially high magnesium, high silica rocks that have a distinct signature. And they're best described really as primitive andesites. And the interpretation is that they're formed from essentially high degrees of melting of depleted metasomatized peridotite at shallow depths. And so this led to this idea that there can be ophiolites that form in the upper plate of a subduction zone. And they're forming essentially because the downgoing plate is diving near vertically and the mantle is upwelling into this gap. And there's rapid extension of that mantle, and you have fluids that are coming from the slab that lead to melting and spreading and formation of what's known as a supra-subduction zone ophiolite, or SSZ ophiolite. And so this was thought as an important recognition to explain the significant amount of extension and lack of volcanic edifices in these settings. So just remember that this is for the in situ igneous origin of an ophiolite, which is found in a mature subduction zone. But at the same time, people were looking at ophiolites exposed on land, and something that they noticed is that beneath the ophiolites, they found a thin package of highly strained metasedimentary rocks. And these were termed the metamorphic souls. And something very strange about these souls is that they have an inverted metamorphic gradient, where at the structurally upper levels, you have very high temperature granulite facies metamorphic rocks that grade downwards into amphibolite, to green schist, and eventually into unmetamorphosed continental slope rocks. And so this was kind of an intriguing thing that people were confused by. And additionally, the shear zone that developed there was thought to be really a mechanism of how it was emplaced. And so there was already an ophiolite that existed, and essentially this soul or shear zone was part of the fact that you had a continent that tried to subduct beneath it, and so the ophiolite was thrusted up onto the continent. So no matter how ophiolites are formed igneously, there's subduction unrelated and subduction related ones. No matter what, ophiolites are intrinsically, they're linked to subduction zones, because either they're formed igneously at a subduction zone, or they're emplaced by a subduction zone. And the reason is because the geologic record's preserved on continents and it's destroyed in the oceans, of course. And so subduction is obviously the primary connection to forming and preserving these in the geologic record. And so that's led to the understanding that there's some important connection here between these metamorphic souls, the ophiolites, and especially early stages of subduction or subduction zone initiation. And so there's a title of a paper that to understand subduction initiation, study forearc crust. To understand forearc crust, study ophiolites. And the reason is because subduction initiation is quite a difficult thing to study. It's an ephemeral process, and so there are very few active examples for us to study of that happening today. There's good suggestion that a lot of the evidence, tectonic, magmatic, and sedimentary response to subduction initiation is actually preserved in forearcs. However, most of those forearcs are deeply submerged in the oceans, and they're buried underneath a lot of sediments, and so they're very hard to sample, very expensive to go out and do these ocean drilling and diving experiments. And lastly, on the other hand, you could study ophiolites on land because they're really well exposed. It's certainly a lot cheaper, but it's very complicated. So as soon as you go out into the Alps and you're walking around, everything like trying to piece together things from the geologic records, a little bit difficult. So if you're familiar with the title of my talk, an analogy might be being Chester and Jesse and waking up after a long night at 6th Street and, looking at a mature subduction zone that occurred, millions of years ago in the geologic past is a little bit about waking up the next morning and trying to figure out exactly what's going on. So I totally would love to be an European Alps geologist, but it's certainly a very complicated place to work. So these forearcs might be really key to preserving that particular record. So in order to form a new subduction zone, you basically have to get a through-going fault through the entire lithosphere. And really that's a balance between the different tectonic forces that are at play. And so one of the main driving forces is slab pull, but if there's not a slab yet, then you don't have that force. And so people have found that with normal lithosphere, that it's really difficult to get a new subduction zone to initiate because the resisting forces are much greater than the driving forces. On the other hand, almost half of the subduction zones that are here that exist today formed with it relatively recently within the Cenozoic. So it kind of suggests that it's a process that happens frequently throughout Earth's time. And so there must be a way for the driving forces to overcome the resisting forces, and that there's a laundry list of weakening processes that help get that done. And one that I'll be thinking about a lot today is about metamorphism. So increasing the negative buoyancy of the slab and increasing that slab pull force. So these have kind of led to several different end members based off these different forcings. And people have classified subduction initiation as either vertically forced or horizontally forced. And so the vertically forced end member is thought to be largely driven by some gravitational instability and internal buoyancy contrast within the system. And on the other hand, you can have horizontally forced, which is thought to be a consequence of long-term far-field external tectonic forces of basically two plates smashing together. And there's a vastly different predicted evolution for those different end members. So if you have a lithospheric slab here with a weak zone, and you undergo this vertically forced scenario, essentially the downgoing plate starts to sink and fall down immediately, and you have mantle upwelling, and essentially the upper plate is undergoing extension, and you're starting to form your SSZ ophiolite right away with spreading in the forearc. On the other hand, in the horizontally forced scenario, you actually accumulate some net convergence between the two plates. And then later, some processes such as increasing the slab pull start to get the slab to sink down. And then you start to undergo extension in the upper plate and have spreading and form your super subduction zone ophiolite. So in the vertical case, you undergo extension immediately. In the horizontal case, there's a delay. And what's happening in that delay is that those forces are being resisted in the horizontal case. And so there are a lot of models that look at the prediction of topography and how things evolve, and that during these initial stages of these two plates colliding, the resistance causes uplift in the forearc, in particular of the overriding plate. And the way that you can tell that a subduction zone has matured is when it gets to this self-sustaining state, and self-sustaining meaning everything's driven by the negative buoyancy of the slab. And that occurs when you go from this resisting and uplift all the way down to essentially a self-sustaining state where you cross over into subsidence. And the change from compression to extension is largely because of those weakening processes and the driving forces increasing. So there are many different ways to study this different process, and the best way is to take a more integrated multidisciplinary approach, because all of them have pros and cons. Like I mentioned, the geologic record is quite scattered, or it's expensive to go sample the forearc of active subduction zones today. People have looked at plate reconstructions and geodynamic models to look at the different timescales and variables that are involved. And also, there's been a lot of seismic tomography studies, which gives you a snapshot in time of its current state, essentially. And I'm obviously been focused mostly on this observational side of things, from the looking at seismic observations, but trying to connect it with the other different ways that are going about studying these processes. So overall, though, the geologic record and most studies are biased towards ancient events, and we don't really have a good understanding of the few events that are happening today. And so that's what I've been working on, is understanding subduction initiation at the Poiseuille margin in New Zealand. So the Poiseuille margin is a very young incipient subduction zone. It's located along the Australian Pacific plate boundary. and the Australian plate is subducting obliquely beneath the Pacific plate. So it's the northernmost segment here of the Australian Pacific plate boundary. And it's a good place to study because Zealandia has this submerged continental lithosphere, but surrounding that is all oceanic lithosphere. And so the past plate motions are really well constrained. The geologic record is not yet strongly overprinted, and there's evidence of very young arc subduction related volcanism. So just zooming in here a bit. So again, the segment is the northernmost portion of this Australian Pacific plate boundary, which is known as the Macquarie Ridge Complex. And there's 4 different segments. Poiseuille is the northernmost segment where there's incipient subduction. The other 2 segments have largely down, right lateral strike slip. And the southernmost segment, the Hjort segment, there's some indications that there's some early underthrusting happening there. And this area for Poiseuille was very sparsely sampled beforehand. So although there's magnetic anomalies everywhere, there really wasn't a good understanding of what was happening across the margin at these particular latitudes. So what you can see on the right here was just the only existing profile that there was before, and some seismicity data. And these seismicity gets much deeper as you go towards the north. And so there's already some indication from the seismicity that there's some temporal change along strike here, that subduction may be more advanced in the north, where you have a deeper slab, and shallower and younger here in the south. So we went there in 2018 and collected a new data set. It's called the South Island Subduction Initiation Experiment. And we got about 1,250 kilometers of multi-channel seismic reflection profiles. And so that gives us a good idea about the subsurface structure. And we also collected 2 profiles with ocean bottom seismic nodes, or seismometers, which gives us information about the subsurface velocity structure and the crustal thicknesses there. So in terms of where we went, here is the incoming plate and the trench. And just a couple features to point out. Just eastward of the trench, there is the Poiseuille fault, which occurs atop of this ridge, this structural high. And this is a right lateral strike slip fault. And there's some active strain partitioning between the trench and this fault. And then behind there's this area called the Solander Basin. And so this is kind of like an active 4-arc basin setting today, but it's kind of weird because it has this different tectonic history in the past, which I'm going to talk about. But we collected a lot of lines throughout this basin because we knew that this is going to be the best place to preserve the record of subduction initiation at this location. So I'm not going to go into basically the analysis of the data in terms of what we found in the regional history. That's work that's already been done, and we submitted it to tectonics. But what we were able to do from all these different lines is come up with a new understanding of the tectonic evolution. And so I'm just going to summarize essentially all that work here, that during the Eocene is when this plate boundary started to develop. And there's about 45 million years where there was an extensional boundary that propagated from south to north. And in the south, because it was largely intra-oceanic rift, you had quickly went to seafloor spreading in this symmetric area of ocean crust. But in the north, where you had these thick continental plateaus, you stretched continental crust and you essentially formed a rift basin here in that Solander Basin. Eventually, the plate motions changed and they started to become more oblique, and that rift basin was cut off. And you had dominantly dextral right lateral strike slip that developed along the plate boundary. So there's a failed rift basin that's preserved here on the upper plate. And you got to your setting of subduction initiation in the middle Miocene around 16 million years. And I'm going to zoom in on that in just a second. But what I'm going to focus in on this talk is everything evolving from the initial underthrusting to the present day structure and how it evolved over time. So this was the setting of subduction initiation. Just to recap, we think that subduction here was highly aided by earlier rifting and strike slip events. So the strike slip essentially caused buoyant continental crust to be translated northward and caused this collisional restraining bend zone. And there was trailing oceanic lithosphere here that was jammed and juxtaposed. So we think that these buoyancy contrasts between thick, low density continental crust and thin, high density oceanic crust was largely important, as well as these existing fault structures that gradually rotated to accommodate shortening. So again, as I mentioned, the history and evolution since this time is preserved in the basin. And one way that we're able to study it really well is because there's a petroleum borehole up here in the northern part of the basin where it penetrated through all of the stratigraphic column. And there's a biostratigraphic age model that was able to be extended throughout the entire basin. So we essentially have seismic horizons that have been mapped throughout the entire basin that have ages on them and are tied to the biostratigraphic age model at this particular well. In terms of the geology of what the well penetrated, there were two finding upward sequences from rifting in the Eocene to finding upwards, and then eventually in the middle Miocene, which again is the time of subduction initiation. There's evidence here that you start to get some coarse material and a lot more sand, and then another finding upward sequence on top of that. So what I'm going to do is I'm going to walk through four really interesting structures in detail that I've taken a closer look at since the regional study, and show you this progression since subduction initiation to the present along the margin. And so in order to do that, I briefly want to introduce the concept of inversion tectonics. The reason being that this was a failed rift basin, and so a lot of the structures that we're looking at have multiple phases of history on them. So a lot of these structures were initially normal faults, and then they were later reactivated as reverse faults. And some key concepts that help us understanding the timing of these tectonic events is looking at the relationships of throw across the fault, and a concept known as the null point, which is essentially the location where there's zero apparent throw across the fault plane. So if you have a normal fault here, and the hanging wall will essentially create more accommodation space, and if you have sediments that are being deposited during tectonic activity, then you'll get this nice fanning geometry where the thickness is increased in the hanging wall. And if that stops and you later subject this area to compression, you'll begin to get reverse motion. And what you'll notice is that as you start to get reverse motion, this null point, which was at the top of this light blue unit here, starts to migrate down the fault plane, and it starts to go down and down and down the more inversion activity that you have. So if you look at this particular snapshot at this moment and looked at the throw of stratigraphic units across the fault, you would see that for the top of light blue here, you have net reverse throw. Here at the top of this darker blue, you have a zero net throw. And for the basement, you have net normal throw. And so that's indicating that there's a phase of normal movement followed by reverse movement. Of course, there's likely to be sedimentation during the thrusting period as well. And another thing that we use besides the concept of null points and apparent throw is looking at the thickness and the stratigraphic patterns that you see for these different units. So here's the same scenario, except that now there's sediment being deposited when you undergo your thrusting period, and the opposite occurs, that the hanging wall now is being uplifted, and so there's decreased accommodation space there, and so you'll either get non-deposition or potentially erosion of the four-limbed and fold crest, and increasing thickness as you go away from there. And so you can see these nice thin thrust units that are being deposited, and this light green one here is one which is occurring after thrusting is finished, where you just get essentially passive onlapping near horizontal onto these tilted beds. And so looking at these onlap relationships is something important as well, to use those three things: the null point, the apparent throw across the fault, the thickness, and the sedimentary architecture of these different units to interpret the tectonic history on these structures. So I'm going to show you four structures, and I'm going to walk through them from south to north. And so they're all located within the Solander Basin. So here's our base map where you can see where these are located. And first, I'm showing you this feature S1 because it's on CC1 line, and it's denoted here by this E. And so it's located just a little bit to the east of this Poiseuille Ridge. And so here's a seismic image that we've pre-stacked depth migrated image. So the y-axis here is in depth. and throwing on the interpretation that we have from these units that have been mapped throughout the basin, we can understand when this fault became active and what the structure looks like. So this black horizon is the top of basement, the red horizon is the top of volcanics, and essentially each one of these other horizons has an age tied to it. And so what we can see looking at this particular structure here is that there's a broad asymmetric fold where it's verging over here towards the west, and these beds are tilting essentially on the back limb back down into the basin. Now, if you look at the thickness of these units and how they vary across the fault plane, they don't vary. There's essentially no variations from the pink all the way up into the yellow. And there isn't any change in any stratal patterns. So this is an example of a structure which we believe is not actually an inverted structure. It's what's known as a fault propagation fold. So that it's a fold forming at the tip of a propagating fault, and that at shallower depths, there's shortening accommodated by folding versus at deeper depths, there's shortening accommodated by brittle faulting and offset. So that can explain the decrease in apparent fault offset as you get to a shallower point, where you essentially get to the null point at the top of this yellow horizon. And so based off the relationships above the yellow, where you have thinning here and essentially onlap over here as well above the orange, we're able to interpret that this structure became active at the yellow horizon, which is around 5 million years, and it's still active today. So it's still uplifting, and you're depositing synth rust sediments out here into the basin that's onlapping and thinning into this uplifted region. Okay, just moving a little bit further towards the northeast here to this structure D. So this is along the CC3 line. And so here we've imaged a structure that is kind of this weird fault bounded doubly verging fold. So it, putting on the interpretation, it looks like it was initially active as a graben. You have downdrop material. It looks like the volcanics are a little bit thicker in this zone, and the period of syn rift strata as well. So these are downdropped. And then as you go up eventually towards shallower depths, we observe 2 null points, and essentially you can see that there's a change from normal offsets up into reverse offsets for a little period. So 2 null points, one at this very shallow point here near orange, and another one down here near green. So it looks like I've painted, essentially what I'm painting onto the fault plane is the magnitude of throw. Sorry, I should have said that on the previous structure. So the blue is normal and the kind of reddish brown is reverse. And so you can see that there's a switch here from normal motion to some reverse motion, and now you have this anticlinal structure. There's some weird changes on this one in the sedimentary thickness, especially in between pink and dark blue. And also it looks like there's potentially normal offsets on this fault and reverse offsets over here on this one at the same stratigraphic level. So that indicates that there's likely some oblique slip or strike slip that's involved at this time too. But overall, the interpretation here is that this was active during rifting periods and then became active as under compression here at green, and that lasted until about the orange horizon because you have this strata that's just capping it and onlapping to that structure. Okay, running again up a little bit further to the north, I'm trying to run through these relatively quickly. There's an interesting structure that's dipping about 60 degrees through the sediments, and it's a really large fault in that it extends down to 20 kilometers depth, but there's not a lot of offsets in the sedimentary column, which is really interesting. But we see reverse offsets on the basement, volcanics, and deepest strata, and a change to, with a null point here, to normal offsets. And the maximum normal offset is actually in between yellow and orange here with another null point at the top. So this is indicating that there's very recent or at least active extension because these normal faults continue up into the seafloor and other normal faults nearby here as well. And so the timing of this particular structure looks like there was activated in compression at the beginning of blue and lasted till shortly after green here. And then now it's currently under a state of extension. So the last structure is up here in the north, and this is by far the largest structure that we image. It's been studied by other multiple other studies as well in the past because this is where that older seismic line was. And so this is known as the Taru fault zone, and it's essentially a multiple sheet fold thrust belt with basement rooted reverse faults. And you can really see really well that you have these thick strata here that are in the anticline. That was clearly when these deposited when these faults were active as normal faults. And then there's a phase of essentially post-rift where things are continuous across the area. And you have these really beautiful thinning here into the fold crest, thickening away on the back limb, all of these classic things that you see in fold and thrust belts under high tectonic rates and sedimentation rates. So overall, there's net 4 kilometers of reverse motion. So there's no null points that we observe. I mean, maybe they're down here in the crust, but you can't image that very well, obviously. So there's net reverse throw on every single stratigraphic level, even these ones that clearly had a lot of normal motion during rifting. And so this is a little bit zoomed out view, but this is really classic what you see in a lot of other places where these limbs are being eroded off, and you also have these wedges that are deposited in between them. And so clearly there's a phase of extension here during rifting, but then things started becoming active after dark blue here, and they continued up until passive onlapping after the green horizon. And so that's summarized here. And these are all qualitative things. So what I'm doing is I'm taking like the net amount of throw and qualitatively saying how much extension or compressional stress there is in the region based off its fault motion activity. And so on this Taru fault zone, you clearly have a major event that's happening right at 16 million years old. This is one of the things that is constraining the timing and location of subduction initiation because it's up here in the north. And so you have a significant amount of activity. And now at the present day state, we don't observe any normal faulting per se, but there is evidence based off the tilting that it's subsided quite a bit and also subsided out here on the flanks. Okay, so I know that was a lot to get through, and I'm happy to talk more about the details of that later, but let me just summarize what this all means. So essentially, based off our interpretation of these different structures, we're able to place timing constraints on the tectonic history throughout the basin. And the arrival of compression shows up in this beautiful wave going from north to south. And so that's consistent with the idea that the subduction has propagated southward over time. So it's consistent with the seismicity data. And if you look at the outline of the slab from seismicity data and peel it back using plate models, the timing of the arrival of compression matches perfectly with where you start to have subduction at that particular location. So before we had these models that had this prediction about this uplift in subsidence, and now we've actually observed it. And so we can verify that that's something that we definitely have evidence for that's happening, but we don't just have like this, 2D prediction over time. We have different locations along strike. And so we can see how the stress state changes basically with time, but also along strike, which is really important. So it's showing this north to south propagation of subduction initiation, giving us rates of about 2 centimeters per year. But also you have to consider that now we're really kind of seeing things in 4 dimensions, which is really important because this is a 4-dimensional process. And so the 2 most important things that we see is that the duration of compression up here in the north is about 8 million years. So that's that lag time that I was talking about, going from compression and then until you go into extension. So that's about 8 million years. As you go towards the south, the duration decreases to about 5 million years. So it gets shorter. Not only that, but it's very clear that the rough magnitude of compression is significantly higher up here in the north, where subduction nucleated, and it decreases a lot as you go towards the south. And so these really suggest that the magnitude and duration of compression decrease, and the interpretation of that is essentially that propagating a subduction zone is much easier. So in the north here, you have nucleation, but once you already have a piece that's undergone metamorphism and you already have an adjacent slab, then that already starts to pull. And so either you have an increase in the driving forces or a decrease in the resisting forces, but that allows things to go faster and more efficient as the subduction evolves along the margin and it's speeding up. So that's the record in the forearc. Now there's an interesting record here in between the basin and the trench. And so there's actually evidence here that there's a piece of trapped oceanic sliver between the trench, Poiseuille Trench, and the strike slip fault that I was mentioning before. And so there's really high subsurface densities that have been constrained by inverse gravity models and also by our seismic velocity models. There's a really high magnetic anomaly that jumps up as soon as you go in this particular zone. And there are some samples that have been dredged there from what's known as like this sliver. And they were diabase and gabbros, and they haven't been dated, but they've been analyzed. And their geochemistry is basically the exact same as the rest of what you find throughout this Macquarie ridge complex. So it's essentially suggests that this is trapped or accreted oceanic lithosphere that's trapped in this tectonic sliver in between the trench and the fault. So that's really interesting, and we definitely need to drill in that area to test. But this is an example of essentially an ophiolite that's abducted onto the margin. And looking at our cross lines now, I'm not going to go into in detail, but you see differences that clearly support this difference along time. And so up in the north here, you have a really thick syn thrust sequence, which decreases as you go towards the south. And of course, at present day, you have active uplift and shortening here in the south. You also see that this oceanic sliver zone is a lot larger, wider and thicker. And as you go towards the south, it gets a lot smaller. And additionally, there are differences that you have a very large and wide accretionary prism and essentially no prism down here in the south. So this, we think, is things that you see different in the margin that are related to its temporal evolution through time. And so there are sediments that are subducting in all of these particular cases that are shown here in this kind of darker blue color. And so you can imagine that this could be a future metamorphic soul that's basically subducting underneath this oceanic sliver here. And so in this case, the soul would be much younger than the material that is here today. So I'll get back to that in a second. But what we've learned from this new understanding about how things progress along strike essentially is that propagation may be the key to forming these plate scale subduction boundaries. That nucleation occurs in a particular place in a small region, and it may or may not be successful, but how these large, boundaries develop essentially as small segments that are linking together and eventually forming a larger plate boundary. And this will get faster and faster if the conditions are right and there are driving forces. So for propagation, these driving forces are significantly greater because you already have an adjacent slab that's pulling, and once it goes, it's going to go off and there's nothing that's stopping it. So eventually, like I mentioned, there's subduction that's happening all the way down here in the south. We suspect that there will be subduction along this entire Macquarie Ridge complex, all the way from the Poiseuille to the Hjort segment in the south. And this is really indicative of this four-dimensional process. So back to these different forcings, and what does it mean for all the other ways that we are studying subduction initiation. So as I mentioned before, people have classically interpreted this IBM volcanic progression as evidence of this vertically forced case. And there's a very rapid 1 million year progression over this massive length scale of 2,400 kilometers. And the only way that these geodynamic models can replicate that is if they have a small horizontal force, but a significant vertical force. And the authors of this study say that it comes from out of the plane. And such a large vertical force that you can see in these cases where you get successful subduction initiation, these forces can only be explained by slab pull, so adjacent slab pull. So essentially, these models, they're not modeling subduction initiation, they're modeling subduction propagation, because if you have to have that slab pull force coming from in and out of the plane, then it's already happening somewhere and it's just propagating to the location that you're modeling. And they also get these ridiculously high plate speeds that are predicted up to 1.5 meters per year, which I'd never heard of in my life before. It seems very high. So one possible factor here is that they're only looking at the upper plate. They're only looking at these magmatic products. They don't have any evidence from the lower plate, and that creates a problem. So it's possible that this whole vertically forced versus horizontally forced thing is really just a difference in subduction nucleation and propagation, where nucleation has more horizontal forces and the vertical forces increase over time once this thing is blasting away at this massive plate boundary and this very fast, rapid progression scale. So in absence of constraints on the lower plate, it's really hard to say. Like, subduction could have already started here, but then the volcanism happened later. And so it's hard to tell whether those melt products are actually robustly constraining the transition to self-sustaining subduction or not. And so what does this mean for sols and ophiolites and how you form these things? So again, the question is, are 4-arc settings indicative of their origin or their emplacement? So the thought process is that if you have a super subduction zone ophiolite, then it must be younger than the metamorphic soul because it's forming above the subduction zone that already exists, right? And the other hand, if you have an emplaced ophiolite, then you would suspect that it would likely be older than the corresponding metamorphic souls that are then later under thrusting beneath it. So again, these souls are very interesting in that they have this very weird pressure temperature path. They have this counterclockwise path. So here's pressure on the y-axis, temperature on the x-axis, and they go in this counterclockwise motion where things are very, very hot at the early stages of subduction, and then eventually they rapidly cool down. So it's thought that the earliest generation of melt should probably correspond to these peak metamorphism. So there's some challenges in the geochronology, as far as I know. I'm just reading in the literature. And part of that is that a lot of the ages of the ophiolite itself are uranium lead ages, and those are restricted mostly to silica-rich differentiates like plagiogranites, and that can occur at a later time. And the other ages that they get, particular for the Sol, are dating of hornblende using argon-argon. And on almost all of these cases, the hornblends are altered, and they're basically high-grade hydrothermal alteration products. And so there's suspicion that that could also occur at a younger stage. And additionally, the closure temperature of this mineral is well below the crystallization age of these host rocks. So you're essentially getting cooling ages, which are absolute minimums. So in both ages of the ophiolite and the Sol, they're systematically biased towards younger ages. So I found it really interesting looking into the Oman ophiolite and what people thought about that, because it's the largest, best preserved, best exposed ophiolite in the world. And in 2016, there was a study that did new uranium lead ages, and they found this overlapping, that the ophiolite and the Sol had overlapping ages around 96 million years. And so that suggested that they formed contemporaneously. On the other hand, there was a recent paper in 2018 in Nature Geoscience, which did new lutetium hafnium dates on garnet. And this was really interesting because they showed that the metamorphic Sol is very consistently, the growth of garnets occurred at 104 million years, 8 million years before the formation of the ophiolite. And they also did uranium lead ages of titanite and zircon in the same sample, and they found that those were consistently at 96. And so this is the first one to conclusively find evidence that the Sol is older than the ophiolite. So what that essentially means is that people were always interpreting the Oman ophiolite as this, it has the chemical characteristics as this supra subduction zone ophiolite, and people were assuming this is, it has to indicate that it's this vertical force case with extension right away. But now there's evidence that there's an actual 8 million year time lag, similar to the time lag that we're seeing in our study as well, so that you have peak garnet metamorphism at 104, and then only later when you start to crystallize the ophiolite at about 96. So essentially, there's a period where you bury the lower plate, there's metamorphism, and as soon as you start to get to that stage, that's when subduction is self-sustaining. That's when it starts to turn on. And then you undergo extension of the upper plate and you start to get cooling and eventually progress into crystallization formation of the ophiolite. On the other hand, what we have shown here in the Poiseuille margin is that we see signatures that there is an abducted ophiolite. So again, subduction formed at this strike slit continent ocean transition plate boundary. And so it looks like that ophiolite oceanic sliver was essentially sheared off from the downgoing plate. And this may preferentially occur during subduction nucleation because of these large horizontal forces. So to just briefly wrap things up, something that's come into consensus from both our study with very good constraints on the past plate motion and how it evolved, and also looking at ancient events, is this is the new subduction initiation database with 13 events in the past 100 million years, and every single event, subduction initiation event, formed nearby an existing subduction zone, so 100% of them. So that suggests that subduction is actually the main driver of subduction. And there are other important factors potentially as well as pre-existing plate boundaries and the affinity of the overriding plate. But essentially, we think that all subduction initiation is forced. It doesn't just happen randomly. This idea that some events were spontaneous is probably not the case. It's just that they don't actually preserve the geologic record of the downgoing plate. And so all they see is this super rapid volcanic progression. And so it appears to be very fast, but they don't have the record of the lower plate, which would suggest that there's a period of forced activity and some possible uplift that maybe is overprinted at other margins. But the structure of the upper plate and those kinematics, those are really likely key, and the early magma genesis and where you get super subduction ophiolites versus where you don't. And we're basically thinking that it's possible that ophiolite abduction is more likely during nucleation because of these horizontal forces and things getting scraped off, whereas forming a super subduction zone ophiolite is probably more likely during subduction propagation, where you have largely vertical forces. And this explains why there's so much little evidence in the geologic record, because subduction's nucleating in one place, and when it's propagating, there's so much vertical forces that everything's just continuing on down into the mantle. And it's very unlikely that things are going to get preserved on the continents. The only way that a lot of these sols get preserved is if soon after they initiate subduction, there's a continent collision. So in the case of Oman, that happened about 5 million years later. So just to conclude, I think the 4 arcs are important to study the uplift and substance history, but also these sols are really interesting. And if there are more accurate geochronology from this Garnet dating, then that's something really interesting to test if a lot of them have older ages than their ophiolites. So I'll stop there. Thanks for listening to that ramble.
Awesome. Thanks for giving that talk. So we'll go ahead and take questions. You can feel free to raise your hand, or you can, it's pretty casual, so you can unmute yourself and just shout it out as well.
Well, I'll say something. That was a really good talk, Brandon. It was great. It's one of my favorite parts of the world. I did have one comment / question. When you were talking about the Hort Trench, Tip Mickle, for his PhD, did see that there was some underthrusting, but not actually subduction. And because of the motion of the plate, motion vectors, it was actually translating that small amount of underthrusting actually northwards, parallel to this to the plate boundary. And so he predicted that it probably never would actually get to be a matter of subduction there. And there is shortening that causes buckling along the rest of the Macquarie Ridge. But I'm wondering, from your work, if it propagates from north to south, whether the orientation of the plate boundary relative to the plate motion vectors is going to cause it to stop at some point, as opposed to propagating all the way down.
Mhm. Yeah, that's a really amazing question. Yeah, I think we totally need to be thinking about this in terms of absolute plate motion as well, and not just the relative plate motion between them. And yeah, I think that's really interesting that there is some underthrusting here in the south, but because of the motion of the plates, it might not proceed. I mean, obviously you do have to have convergence across this boundary. And I think something that's insightful is that the Australian plate is huge. It's a giant plate and it's moving very fast. And so, yes, we do see this at this very small segment scale at Voisiger, but it's very unlikely at this stage to have an impact on like the entire Australian plate because it's just such a small segment. So I think we're seeing like the very, very early stages of nucleation. And it's possible that this happens throughout Earth's history a lot, like one little patch is subducting, but you probably have to link up a lot of these boundaries in order to have a really big change on plate motion. And clearly that's, maybe what happened in the Pacific where you see a really big change in the plate motion at the same time as you have the IBM system start to kick off. So yeah, whatever happened with IBM, for whether everything was right with this propagation, it affected a very large plate, and it was a lot bigger scale than what we see in New Zealand.
It was very, very interesting. Curious to see what happens. I won't live long enough to see the plate move, but
exactly.
Nonetheless, thank you.
Yeah. Thanks.
Awesome. Any other questions?
Yeah, hi, this is Ian Norton. I got a question. The
Hey,
Tethyan ophiolites like Troodos and Oman and the ones up in the Himalayas, they all seem to have been abducted within 10 to 20 million years of the formation of the oceanic crust. Whereas this one down in New Zealand looks like it's really old ocean crust. Do you have a compilation similar to this map of age of ophiolite versus abduction? I'm not sure if you learn anything from it, but it is an interesting observation.
Yeah, so I've been thinking about this a lot lately, and that's a really good point. And I definitely think that there is some correlation. Like you said, the classic kind of Tethyan style, they seem to be abducted very quickly after subduction initiation. And I think based off reading in literature and what we know, that that's probably because the subduction zone is still very warm. And so there's some studies that suggest that the reason that you get abduction and exhumation is because it's so warm and that rocks are preferentially transferred and essentially exhumed in those particular settings. Whereas once things are cold, then you might have some off scraping, but it's very unlikely that you're going to transfer a lot of material. So in New Zealand, it's not necessarily very young because this oceanic crust formed just to the south along the spreading center and then was translated to the north during strike slip. So we think that it was scraped off at the very, very early stages of subduction. And so it was probably only about maybe 10 million years old or even less when this was scraped off essentially. So it's probably still young, warm and buoyant and able to be kind of transferred over.
All right, interesting, thanks.
Yeah, thanks.
Brennan, this is Ian DL. Can you hear me okay?
Yeah, I can hear you loud and clear. Hi, Ian.
Just an observation about the Andean ophiolites, the Roccas Verdes Basin in the south. It's a sort of variation on the theme that you were mentioning about the vertical pool, that there it seems that the actual development of the ophiolites started with some subduction, but before arc magmatism. You have a margin that's been subducting for 500 million years off and on, most recently in the Permian, most recently compared with the late Jurassic, early Cretaceous ophiolite formation. So it seems probably the weight of the downgoing slab was helping to the extension in the supra-subduction zone, but the actual ophiolite was formed before arc magmatism got reinitiated. And then the ophiolite got preserved when South America started to move faster forward in a mantle reference frame in the mid-Cretaceous. And then you got the soul forming and the ophiolite being preserved.
So the ophiolite was already still forming in the upper plate though, right?
Yes, it was forming in the upper plate, and the arc started and filled in the basin, the marginal basin, but it wasn't started before when the actual ophiolite was starting to form. So it was super subduction zone, but pre-arc.
Yeah, I think that's probably consistent with a lot of the ideas. That people have is that the supersubduction part is really at the very early stages because it's really hot and the mantle is flowing into this gap, and you have fluids that are coming off of the slab into this very shallow portion, and that's what's forming the ophiolite. But later, as subduction progresses, then the downgoing plate is now cooler, and so eventually you fill in this portion here once things start to refrigerate and get cold over time as subduction matures, and then you transition into like calc-alkaline, classic arc lavas, and those are kind of a little bit further over. So yeah, I think that's probably a consistent idea with that like temperature change that a lot of people are thinking about.
Yeah. Anyway, excellent talk. Thank you.
Thanks, Ian. Appreciate it.
So I have a potentially stupid question, but since this is a discussion hour, I thought I'd just ask. So I haven't thought too much about the metamorphic soul, but I always thought of it as kind of the, the surface that the ophiolite is transported onto, the final location. So to me, it just seems counterintuitive how it can be so much older than the ophiolite itself. Can you explain that?
Yeah, so I don't have a good image here of Oman. Sorry, I'm bouncing around here. So let me just go. So yeah, I think those were some of the more initial ideas, is that basically it was the sediments on the continental margin that basically got overthrust by the ophiolite. But based off, and I'm not obviously an expert in this in any way, the metamorphic facies of the soul, they're saying that it forms at very high temperatures and at depths of around 45 kilometers. So the soul had to be, actually I do have it here. So the soul was essentially initially subducted very deep and experienced like granulite facies, I think temperatures of like 900 degrees and 15 kilobars pressure, and then must have come back up and gotten welded to the ophiolite. The thing that's weird is that Oman is only 10 to 12 kilometers thick, and they say the soul was down at 45 kilometers. So it's unclear, at least that I know of, like what happened to that roughly, 25 kilometers or so that was in between. Did it just disappear or get chopped up by later tectonics, or what happened? So yeah, I'm not really sure.
Yeah, that's kind of the same train of thought that I usually have, and then I just run into a wall. But maybe some tectonicists know what's going on better than us. Thanks, though.
Yeah, it seems like to preserve the soul, like it has to be really warm, and so it's like welded and it's buoyant to the upper plate, or a continental margin comes in later and like pushes it up. So I would love for more people in this field to be looking into like the like the age of these souls. I think that'd be really cool.
Thanks.
Awesome. Well, I think that's all the time we have. That was a really enjoyable discussion hour. So thank you, Brandon.
Fantastic.
And so
thanks everyone for the questions.
Yeah, really good questions too. And so next week we'll hear from more alumni. So we have Anna Ramirez and her team from IHS Market. So be sure to check that out. Have a good rest of the week, guys.